All right. Wow, there's a step. How you guys doing? Good, good. Yeah, sweet. I saw there's all sorts of hatred about aggregating histograms, and I'm sorry. But I have some things to say about that. About 3 years ago, actually, no, 2 years ago, 2.5-ish, I was sitting in a room of 300 engineers at Netflix, and Neil Hunt, our head of product development and all of our product, made the mistake of asking us if we have any questions. And I said, oh, yeah, me. And he called on me, which is another big mistake. And I said, Neil, what do you think about Netflix regarding the part of the world where we have never been? The part, at this time, we weren't global. And out in that part of the world, there's 3G connections, and there's cellular, and there's devices that are terrifying. They terrify me. They kept me up at night. And I said, what are we going to do to go after that world? And Neil said, well, yeah, you know, this, that, the other thing. But what you're talking about, that's at least 5 to 7 years off. It's 5 to 7 years before we can build a truly global product that really works kind of everywhere. And I said, Neil, that's great, because I would like to invite you to come to Hack Day in 3 weeks, and I will show it to you. So gauntlet taken, thrown, everyone heard it rattle in the auditorium. They're like, what are you doing? He's the head of product. I said, don't worry about it, because here it is, 3G in Kazakhstan. I actually went to Kazakhstan. This has the Kazakh plates on it. This is a field in the middle of absolutely nowhere with a TV hooked up to an inverter. Turns out the Russian word for that is inverter. I had a little bit of trouble trying to order that. And Kazakh man here actually doesn't speak a word of English. And he just saw me pop this SIM card in and hook the thing up, and boom. And he goes, well, where do I buy this Netflix SIM card? And I said, well, it's a VPN. Nothing it's coming soon. It's coming soon. We're working on it, and I want to talk today about how we do that. So I said, look, we're going to have to deal with the internet that you guys have out here and in all of the parts of the world where we did not develop our app. We developed it. We were mostly in the US, and as Roy mentioned earlier today, you know, we even went into Canada, and we called that international, but it was not a scary step from a network perspective. And it's going to take a long time for that to start getting better as we started to get out into the edge, as we started to go out into the different parts of the world. And we saw that the global internet, it's getting faster. People are putting in better links. There's fiber going everywhere, better equipment. But it's also getting slower at the same time, because while all those links are there and, you know, these companies are doing a great job selling service, everyone starts using it. And then what do you get? Wonderful congestion and all the other wonders that you get. And so I was taking the attitude with Neil that don't wait for it. Okay, let's just go and build the thing as it stands, and let's deal with it how it's there. But in order to do that, we're going to have to build a pretty good picture of what the internet looks like. We're going to have to understand where it's really bad, where it's bad in regard to our product, and that meant logging all the things. And when you start talking about logging all the things with the global Netflix base, you're talking about a lot of traffic, which is why Adrian Cockcroft once joked that we're actually just a telemetry company. We just log stuff all day. And then occasionally there's media that comes off the CDN. But we need to log this without averages. And we need to be able to see what that distribution looks like. And we need to size it up and build a product that's going to address those markets. So, of course, two things pop up right away, right? The first is you want to go for the average. The average says, that's great, except that it doesn't really let you see what the distribution looks like. You just see where the average happens to be. And you go, well, on average, it looks all right. I don't know. And the outliers that you get in that logging are going to really heavily distort your average. So the stuff that, you know, kind of goes into the infinite bucket and takes a really long time, and the stuff that goes into the zero bucket, maybe it's a cache hit or something like that, where times are, in this case, I was logging various network measures. Sometimes I would get negative values from clients, and that would really just blow out the average when I started looking at it. So you can take another approach. You can try to sample everything. And you can say, all right, well, that's pretty good when I happen to hit the issue that I have in that sample, which I may or may not, given how I choose the sampling population. If I just sample a percentage of requests, I might miss some device behavior. If I sample across devices, I mean, there's issues there, especially when you're talking about rare events, which might just blow up the experience, because something that's rare that happens on a network, if you're running a heavy network application like Netflix, you're running thousands of connections, while you're actually building your product. So it's rare things seem to be pretty frequent. And the problems aren't sort of equally probable. So instead of that, I said to myself after hearing an inspired talk that why don't we just aggregate the data? Why don't we build a massive MapReduce machine out of all of the clients that are in the world? So the TV devices, the cell phones, everything. Everything that wants to run Netflix, let's use it as part of the free compute power that I can take advantage of, as long as I don't get in the way of the user experience, and send back, do some aggregation and send back the aggregated data. So based on that, we went and sized up the internet with all this infinite free computing power, free in the sense that you'd better not bust the app experience, but free in that you're not paying for it on AWS or whatever service you happen to be using. And this is really good because when I've got very fast metrics, so in the case of networking where I was interested in the network performance, or say key responsiveness, like when the user clicks down, how long am I waiting? These things are happening very frequently. And one of the nice side effects about my favorite aggregation technique, the histogram, big surprise, is that it's flat in memory use and it has relatively low insertion time. So I can put that data together sort of in real time. I can filter out the stuff that's not helping me, say I'm getting a bunch of zero counts or whatever, and then I can emit an aggregated log blob. And I say, look, this is what happened. So for those who haven't seen it, this is actually measuring curl requests going to a website that happens to be on the far side of the world. And here I'm building the histogram as I go. And I see that most of my times are actually right here, kind of in the beginning, so that this is pretty good on average. But I also start getting a whole bunch of outliers in the distribution. And for any non-trivial set of events, this is probably going to happen to you. And those outliers are really just going to pull the entire thing over. So once I've got that histogram, now I have an idea of what the shape looks like. Then I can say, I can do a little bit of not so fancy math, which sounds scarier than it is. I can take the inverse empirical cumulative distribution function of that, and I can calculate all of my percentiles. And that's done by a very simple equation. So we take f of the n to t, and then we multiply, anyway, some stuff. But you can actually just plug it into R, which will do all the work for you in 2 lines of code. And great job, John, for introducing R earlier today. And I can pop out this wonderful function, what I'm calling here the IECDF. So based on the histogram, I can say, I've now got a function that I can say, show me where 50 percentile is, where's my median, show me where the 95th percentile is, and this happens to be the numbers for the histogram that you just saw. Which is kind of great, except that I'm wasting all sorts of space there on a part of the graph that I'm not that interested in. I have, in my sort of flat histogram, I've got equal distribution between the buckets. So the buckets are all the same size. And that's great at sort of my area of interest. This blue dotted line is my median, and I just overlaid it for simplicity here. And the red line is my 95th percentile. And I've got a lot of resolution where I'm sort of interested, but I don't have a ton of resolution. Well, I have exactly the same amount of resolution out on my tail, which is a bit of a bummer because these requests, they're slow, but I'm not exactly interested in how slow they are. I just need to know that how many slow requests are kind of happening. So I could afford to have less resolution there if I cut that correctly. So voila, Google gave us the answer. They said, hey, you could use exponentially spaced binning. So again, still a constant binning algorithm, but here I'm putting all of my resolution in sort of the area that I want over here on the left. But as I get out to sort of the extremes, I get out and space my buckets out wider where I don't need as much exact precision about what I'm measuring. And it turns out that I get almost exactly the same 50th percentile and 95th percentile. And there's some math that was shown to you a little bit earlier about why that works. But the quick takeaway is that it's actually very cheap to compute when you're all the way out in your client, and you can measure it everywhere in the world. So I never want to hear from people, oh, we can't log that because it's moving too fast, or there's going to be too much log data for this really important thing that we need to make a decision. BS, okay? Forget it. You can absolutely log all the things. You don't need to emit one log for every network request that you make, but you can actually do it and capture all of the data in a really small chunk. And if you want to get a little fancy, you can wrap that up in a protobuf and save yourself a little bit more space. Which leads to this wonderful amount of data that you now have, and I'm a firm believer that data is better than opinions. I happen to get a lot of opinions when we're having these sorts of debates internally, and these are all actual quotes, but protect the innocent here. But the first one that really got me fired up was, well, Guy, we live in a 50 millisecond world. Does that seem strange to anyone? 50 milliseconds across the world. I mean, your first slide that I showed you, which was somewhere in China, happened to be more than 50 milliseconds on just about every single request. Better to have the data. Well, people that load up the application, they don't really mind if there's a spinner there while we're loading up all the stuff underneath. That's fine. I mean, why should we do that instead of investing in, some cool feature that we happen to want to really build? Or there's no way that the client is making that many requests to our servers, which this one actually really baffles me because, you guys are a monitoring audience, and you've seen the kind of monitoring in which actually Roy gave you a little tease earlier today. You've probably seen some of our tools, and we have tons of metrics. And it baffles me they could look at all the server metrics and say, well, no, there's no way that all those requests are happening. When you just divide the number of requests there by the number of clients, and you go, come on. It stands to reason. But the moral of the story is that it doesn't really matter what you pick. Any architecture that you work with for any sort of interesting problem like this, it's going to be hard. So it helps to make it cheap in order to be able to experiment live in the wild and actually see what the real experience is. And as soon as you do that, you're going to need to aggregate all those histograms. No one's arguing? Oh, that's a surprise. The key there is actually, it's a little bit of a nuance to what I was saying earlier. You don't aggregate the percentiles. You'll get yourself into a little, that's fine for estimating work, and actually it's almost always wrong. So I do actually agree with Megan on that one. But you can actually take the counts, put them together, and come up with some, without really incurring any more error if you're dealing with the same sorts of binning. And you can see kind of what happens. So in the data list dash that I've got here, this is just a view on all of that logging data that I showed earlier. Towards the top, we have requests that finish fast. This is DNS. I just picked one metric to look at. So this is how long the client takes to resolve DNS. No artificial server measures about, oh, our DNS servers answered this quick. No. I want to know when it got to Kazakhstan. Okay? I need to know on that TV how much time was blocking on DNS, because I need to architect based on that. And then as I get kind of slower, you'll notice some banding here, some different resolvers. They show a nice band sort of in the middle. That's by host. That's because we do a few redirects sometimes, some CNAMEs we might not want to do. And then down here at the bottom are sort of timeouts. Our client actually kind of kills this around that period. So this actually looks pretty good. And here I'm showing the histograms for each hour of the day in sort of local time. So that's fine, right? I've got all the I've got multi-dimensional histograms here where I can see how this changes. So if I get to a congested window, I can see, oh man, now that really kind of spiked. But this was really well behaved, except that was the US, which is where we built the product, and it was great until we looked at somewhere else. And magically, the opinions were soaring at work, except there was data. And so I said, well, that's bad. That's the technical mathematical term for that. That's bad. And we're going to have to engineer around that. So it helps if you know what that is before you try to engineer around it. But it's actually really cheap to measure. So once again, I can pop out my IECDF, and I can say, great, from these histograms that you already sent up to me, tell me where my 50th, my 95th, my 99th is. If somebody argues with you and they say, no, I want to see the 99th, okay, I can calculate that. I've got a function that gives it to me. I can pick any percentile I want. And then I can cluster that and get some similar experiences based on some automatic clustering. And I get my wondrous bubbles, which are great. So bubbles here, this is actually showing you on, again, DNS time, the 50th percentile of requests versus the 95th percentile of requests per ISP. So if I want to try to get a sense of how are different networks and where do I want to conduct some network tests in the wild with a real product, I can now cluster them and say, okay, well, there's these green guys down here. They're fine. I mean, that's that looks okay, because what I want to sort of see in this graph visually is how far away is my 95th percentile from my 50th percentile. Because if it's really far away, I got some issues. Okay, that's going to be probably a pretty congested network. If it's relatively close, the latency might be high, but it's consistent. So I know that everything's going to get there, and I don't need to go chasing it. So I call this instability. I'm not the first one. Other people called it that. And I can see way up at the top there in that purple, it's actually so far out that it just blew out my scale, so I couldn't really show you what was going on down here until I blew that up. But it was one of those cases where those ISPs, they're going to be really hard to work with, and it's going to be challenging to figure out how to get the product to work there. Again, I can see this as kind of a blow up of the bottom left, and I've got the green population, and I have to leave these ISPs nameless to protect the innocent. Nick, you're doing a great job wherever you happen to be in the world. And he is down there on the bottom left. And sort of as I kind of go up, I start seeing different network properties of instability into the orange cluster, which might be a little bit better if I want to try to progressively get my application to work in more and more parts of the world. And that's all great, but the data that I just showed you was smart TVs. What's wrong with smart TVs? Well, actually, don't answer that. I used to be an engineer in TV, so I look at any smart TV and I'm like, you have the following 18 bugs. So, but anyway, I do try to actually watch the TV sometimes. I'm just not good at it. And smart TVs have the property of, they typically have a little bit of demographic bias. So people who tend to have a smart TV, they usually have some income, they usually buy a decent internet connection, and things are actually not as scary as, say, when you're on a really low-end brand name you've never heard of Android kind of phone. And it's running over the cheapest cellular plan that you can possibly get. And then these numbers look a lot worse. So this is actually the Android data that I'm showing here. And again, the 95th really runs away from the 50th on some of these networks. So now we know where to look. Now we know where to randomize. Now we know where to study. So now that I know that, I have to make it easy to go there. Right? I can tell you that actually not too many of those networks happen to be in Kazakhstan. So it turned out that wasn't the scariest thing that I was looking at in our data set. So I could jump on a plane and I can head over there and I could bring a TV and get an inverter. And I can hook all that up and show the guy and he'll say, great, I want to buy this Netflix SIM card. But that's expensive, and that costs a lot for your engineers. I can also abstractly analyze the data the way we were just kind of doing it. And I can get a sense of the numbers, except that always sort of fails the reality. It never really puts you in the shoes of your consumer. You don't see it. And my last alternative is I can actually take there and I can bring it here. I can actually model the reality based on the experiences that I'm seeing with my customers, and that's what I call a reality lab. Now, this is my version of practical teleportation. I'm still waiting for the physicists and some of our CERN friends who are talking tomorrow to figure this out. But for right now, I can make it possible to, I can use one of these services and pay somebody to actually try the app out and look at how their connections are working. Or I can go and I can try to simulate it. And one of the first networks that I tried to simulate was one of our better behaved networks. And I was, relatively naive and new at the company, and I said, this is the Orange network in France, and that's great, until I ran into one of my French colleagues who said to me, no, Guy, this is not Orange, this is Orange. And so I fixed the title, and I said, sorry, I spelled it wrong, I just didn't really know. So aside from plugging a display into a router, which is a little bit of kernel fun that I will share with you, I just need to clean up the patches a little bit before I send them upstream. This is actually just a normal, regular router where I started playing around with sort of the network shaping to try to make it match the reality that I've measured from my actual devices. So is anybody here familiar with TC, the traffic cop stack? Well, some people, or DummyNet, the FreeBSD version that it was based on. So this lets you pretty much do anything you want in terms of network shaping, and it's really great at that. It lets you, put packets out of order, it lets you drop packets, it lets you shape them based on correlations. I mean, it's really a very sophisticated tool. But The moral of the story, I'm going to get that to you as soon as I can get it working. I just started that project. But the best thing that I'd love you to take away is don't guess. Don't try to guess what the users are doing. Don't try to build really complicated architectures without trying to measure some of this stuff. And I know you people are not the criminals of that. Some of my developer brethren. Anyway, when we actually base this stuff on real data, then we're going to end up building better software that's going to kind of reflect what happens in reality. So it doesn't need to be scary. Thank you very much, and I appreciate your time.